applications, element options can be modified when necessary to solve a wide variety of challenging problems. As I scroll down the element family list, you can see the various specialized element types available in Abacus, including some for solving non-structural applications, such as heat transfer and thermal electrical analysis. Next, I will associate the stent geometry with a predefined material from nitinol. I will open nitinol in the material editor, which provides access to the vast material library in Abacus. The constitutive models range from simple linear elastic behavior to complex, highly nonlinear behavior, such as that of nitinol and the arterial tissues simulated in this example. Next, I will modify the balloon part. The focus of this analysis is the behavior of the stent and artery, so I will convert the balloon into a single shell surface that will contact the stent. More detailed modeling of the balloon could be added for future analyses. Rather than show you all of the operations required to create the stent model, I will now switch to a version of the model which I have completed in advance. Here is the assembly, and you can see that all the parts are now meshed. The analysis is split up into two steps. In the first step, an internal pressure is applied to the artery, as indicated by these pink arrows. Axial tension is also applied to the end of the modeled artery segment. In the second step of the analysis, a boundary condition is used to expand the balloon in the radial direction, as shown by these orange arrows. Next, I will highlight the contact interactions, one of which models contact between the balloon and the stent, the other of which models contact between the stent and the artery. Abacus contains a powerful set of options for modeling contact effectively in a wide variety of applications. In this example, both contact interactions include friction. Now that you have seen the primary features of the model, let's take a look at the results. I will modify some display settings so we can visualize the entire stent, not just the portion modeled. When I animate the results, we can see the stent expand into the artery wall. Next, we will take a look at the stresses in the stent. I will remove the artery from the display and deactivate translucency so that we can clearly see the stress contours on the stent. I will zoom in on this connection region, which is an area of high stress when the stent is expanded. A proposed design change for this stent, which we will investigate, is to widen this connection. So that we can return to this contour plot later, I will continue working with a new Abacus CAE viewport. Here is the model with the narrow connections between the loops of the stent. I will now switch back to SolidWorks. In SolidWorks, here is the sketch that includes the dimension for the connection that I will be modifying. I will edit the sketch and double the width of the connection. Once SolidWorks rebuilds the assembly, we can see that the connections between the loops of the stent are now twice as wide as those of the stent we analyzed originally. Now, I will re-export the assembly into Abacus. The associative import functionality will update the assembly in Abacus CAE with the new stent geometry. All the analysis features I defined on the stent are maintained after the design modification. I ran this analysis in advance so we can examine the results of the design modification. As before, I will remove the artery from the display and contour stresses on the stent. I will arrange the two viewports so that we can see the results of the original analysis in the upper viewport and the results of the new analysis in the lower viewport. With the viewports linked, I can synchronize the view of both viewports and zoom in on the region of the design change. Now we can see that increasing the width of the connection between the stent loops does not have a significant effect on the stress around the connection. If anything, the stresses in this region are slightly higher after the design modification. I hope you now have a better understanding of how you can use Abacus to perform complex nonlinear analyses on SolidWorks assemblies.
So I hope you enjoyed a view of how these products look and behave. To summarize our presentation today, SolidWorks Simulation, Simuli Abacus, and Simuli Abacus SolidWorks Associative Interface together is a very powerful and complete solution for sophisticated engineering problems covering a vast spectrum of industrial applications. SolidWorks Simulation and Abacus FEA can support the needs of both non-expert and expert users across all FEA domains. SolidWorks Associative Interface eliminates rework as geometric changes in SolidWorks propagate with no loss of analysis features to Abacus. And lastly, speed, accuracy, and flexibility are just three of the many reasons customers choose Simuli Abacus for their FEA needs. On behalf of Atul Gupta, John Weaning, I'm Howie Distel with Dassault Systems, and we thank you very much for your attention today. Have a great day, everyone.